In lesson 6.3, volume using the shell method, we'll explore another way to find volume of solids of revolution, much like the one I have right here in my hand. Kind of looks like a parabolic kind of solid here. And in lesson 6.2, we found the volume of shapes like this using what we call the disc and washer method. However, here in lesson 6.3, we're going to chop this shape up in a different kind of way and find the same volume, but using a different method called the shell method. Now, when we talk about shells, what we're really talking about is hollow cylinders. And all of these shapes can be decomposed into a series of these hollow cylinders, and we can find the volume that way. So that's what we're going to explore in this lesson. We're also going to compare and contrast using the shell method to using the disc and washer method that we just learned in the last section. We'll learn that sometimes the disc and washer method is far, far easier. And likewise, we'll find that the shell method is itself sometimes far, far easier. It's really up to experience to say which is better when. But after this lesson, you will have that experience and you'll be able to tell for yourself. So before we get any further, why don't we first take a look at a few solids of revolution, get into the formulas that we're going to use in order to find the volumes of these cylindrical empty shells, and then we'll take a look at a few examples and see how this all fits together. And it will fit together quite nicely. So without further ado, let's take a look at some formulas and some solids. Alright, so before we get into any formulas, let me first show you what we're going to do by talking about this cylindrical shell method. The solid that I'm showing you right here almost looks like the top half of a donut, if you will. It's kind of rounded and has a hole in the middle, as you can see. So essentially, all we're going to be doing here is separating this solid into a bunch of shells, hence the name of the method, the shell method. And of course, in this particular example, I only have a finite number of shells. But in the actual calculus that we'll be doing, we're going to pretend like we have an infinite number of shells, and all we're going to do is add up their surface area. That will accumulate up to the volume of the whole solid. Now, looking at these shells, you might be saying, well, what solid exactly is that? But of course, if I put all of these shells together, what I would come back to is the exact solid that I started with. So there you go. And that's pretty much what we're going to be doing. Now, the shell method works really well on something like this because I wouldn't want to find the outer radius and inner radius for each disc or washer that I could slice this into. That would be especially tedious. However, there are other examples, similar to the example I showed you before, this paraboloid, if we look at it this way. I'm going to look at it straight up, why not? But this, if we were to divide it into a number of shells, could get unwieldy. There's no hole in the middle, and finding the outer radius probably is not all that bad. But I do have an example of what this would look like if it were divided into a bunch of shells. Now, if I put this down here, you can see that what I can do is I can remove a couple shells here from the outside. In fact, I can remove another shell from what's left of the outside. And essentially what's happening here is I'm working my way in. Here's another shell, and working my way in, and in, and in. And eventually I end up with a bunch of empty shells. Now, because there was no hole in the middle of this, the middle piece does appear to be solid. But of course, using calculus, there would be no solids at all. They would all be shells, cylindrical shells. And so all I really need to do is find the surface area of each one of these shells. And if I add those surface areas together, all of the surface areas together, what I will eventually end up with would be the volume of the complete solid that I started off with. In this case, my solid would look like that, which you can see is a bunch of shells that simply approximates that. So that being said, before we get to the formulas, consider what you think the formulas might look like. As I said, they are the surface areas of these cylinders. And so that being said, do you know how to find the surface area of a cylinder? Well, here's how it's basically going to go. What we're going to do is let's begin with pretending that we have a vertical axis of rotation. And what that means is that if this is my axis, perhaps I have a function, and I'm going to make this function up here, but perhaps I have a function that looks something like this. Maybe it goes like that, and it's bounded above as so. Now, if I want to rotate this around a vertical axis, and what that means is that it'll look something like this. Well, the other side of that, of course, would look like this. Now, perhaps this would be best done using the washers or discs. Nevertheless, let's go ahead and pretend like we're doing this using a shell method. And if I do that, let me draw a representative shell. It might look something like this. And, of course, it does have some depth to it. So perhaps my shell looks something like that. Now, that's a terrible drawing, but hopefully you get the point here. How wide is each shell? Before we begin talking about the radius and the height and all that, how wide is each shell? Well, in this particular example, the width of the shell is going to be dx. And what that means is that everything here needs to be in terms of x. All right, so if I do that, remember that the surface area of a cylinder is actually nothing more than the circumference of the circle multiplied by the height. Now, of course, 2 pi is a constant, so all I really need to deal with here is what is the radius and what is the height. Now, in this particular example, because I'm spinning it around the y-axis, which is, x equals 0, my radius here would simply be x. But to generalize, what it would generally be would be a minus x, where a is the axis of revolution. Now, the height, of course, is just going to be the function. And in this particular case, of course, because there's empty area underneath, this particular case, the height would actually be b minus f of x, where b is the upper bound right here. So it takes a lot of getting used to, but really in each problem, all you need to do is figure out, is this a dx or a dy problem? And once you know that, just get everything in terms of x or y accordingly. If we do that, the 2 pi, since we said it's a constant, it can go outside, and all we're left with inside is the radius, which may be a function of x, and the height, which also may be a function of x. So that's kind of squished together there, but essentially all it says is 2 pi r h. And there's the width of each shell. So if we're doing a horizontal axis, I'm not going to go through all the rigmarole again here, but if we're taking this same region here and rotating it over the horizontal axis, well, in this particular case, notice what would happen. Our shells this time would be horizontal, and I'll try to draw a better shell this time than I did last time. Actually, that's not too bad. What is the width of each shell this time around? This time, the width is dy. And so what I'm going to end up with here is the volume will be 2 pi. I'll still go from A to B. Now remember that A represents the axis of rotation. So we're not going from A to B this way. In this particular case, this is not A. Rather, this is A. So from the axis of rotation to the outside AB, this will be the radius as a function of y, the height as a function of y, and then, of course, the width of each shell, which in this case is dy. So, that's the formula for the solids of revolution. Let's go ahead and actually try an example now. Let's go ahead and move on to example A, which I promise will be fun and exciting. So here in example A, we're given a region, which you can see here in the notes or on your paper. And according to the directions, we're going to take this region and revolve it around the y-axis. Now, if we do that, what we're going to end up with is a solid that we see here. And you can see that essentially what it is a cylinder with a kind of a depression dug out of it. It could almost be represented as almost like a cereal bowl, if you will. And what we need to do is find the volume of the material used to create this cereal bowl. Not the volume of cereal it can contain, but rather the volume of the actual solid itself. And so to do this, the first thing that we really should do is take a look at this picture and determine, are we talking about a dx problem or a dy kind of problem? Well, if you take a look at this, I'm going to go ahead and draw a sample shell here, and there it is. You can see that the sample shell has a width of dx. That is, it is in the x direction, its width. And so that tells me that everything in this problem has to be relative to x. Well, that's actually pretty fortunate because the function we were given is in terms of x anyhow, so hopefully that'll make this easy to deal with. There's really only two things that we need to determine. We need to determine the radius function, and we need to determine the height function. If we can get both of these, then we can set up our formula for using the shell method to come up with the volume. So what is the radius of any shell that I draw on this solid? Well, the axis of revolution is x equals 0. That is the y-axis. And going out from there, we're going to go out 2 units on the x. And essentially, once I'm at the beginning where x is 0, there's a radius of 0. And once I'm on the very outside shell, it has a at x equals 2, that has a radius of 2. And in fact, the radius for this is just the function x. And that will always be the case so long as we're revolving around the x or y axis. So long as we're doing that, the radius will just be x or y. Now, the height in this situation, the height of the shell, it's going to start at 0, and it's going to go up to, well, how high? That is actually going to make use of our function that we're given right here. Our height is actually going to be 1/4 x cubed. And you can see that when x is 0, our shell has a height of 0. And when x is 2, it looks like the height of our shell will also be 2, which if you feed it through this height formula, you'll see that that is the case. And so now that we know all this great stuff, let's go ahead and set up our formula. Volume is going to be 2 times pi times the radius times the height. So I'm just going to go ahead and lay it all out here without simplification. We should include our dx because that's the width of each shell. Now, where are we starting and where are we going? Well, our lower bound is actually going to be our axis of revolution. That's just going to be 0. And we're going to go out to x equals 2. So don't think that we're going from -2 to +2. That's not the case. We're just going from 0 to 2. You can think of it as we're really only going halfway on the shells, if that helps you to see it. So anyhow, we can go ahead and simplify this a little bit. We'll have 2 pi from 0 to 2 of 1/4 x to the 4th dx. And I'm not going to go through the entire process of integrating that. I'm hoping that you can do that yourself. And if you do it correctly, what you should end up with is 16 pi over 5 cubic units. And so it's an easy integral to do. Quite honestly, you could do this in your calculator if this was a calculator-based question, which it probably would be. And we would end up with 16 pi over 5 units cubed. So it really was not all that bad. I want you to consider how you would do this using the washer or disc method. Of course, we'd have an outer radius, which would be 2 for each washer, and we would have an inner radius, which we would have to solve for because it would have to be in terms of y. So perhaps it would be something like the cube root of 4y. It would just get nasty. And in a situation like this, the shell method is certainly much, much better to use. So that being said, let's go ahead and take a look at another example. This will be example B, where we will do a revolution over the x-axis. And in this next example, there will be no hole. It will almost be like this paraboloid that we started this entire lesson with. Let's go ahead and take a look now. So here in example B, we're going to repeat essentially the same thing we did back in example A with a couple differences. Of course, we have a different equation to work with here. In fact, if you look carefully, this equation is not even a function. But that shouldn't be too much of an issue because it still gives us a region and we're still revolving it. There's our second difference. This time we're revolving it around the x-axis rather than the y-axis. So maybe what we'll end up with is another paraboloid kind of shape, more or less like that. Maybe less because it's a little bit thinner where my fingers are, and it's a little bit longer. But essentially the idea is there. So, there is a picture of the graph we're going to be revolving. We will revolve it around the x-axis, and to get that solid that you see. Now, the first thing we should do to determine whether we're dealing with an x or y kind of problem here is to draw a representative cylindrical shell. And so, I've done that for you right there. And now we can go ahead and take a look at it and say, well, the width of this cylindrical shell is a dy kind of situation here. The width is simply the width of this black line here. Alright, so we are dealing with y's. That means that our radius, our height, everything in this problem must be in terms of y. So let's begin by finding our radius. Fortunately, because we are revolving around the x-axis, our radius is actually just going to be y. And you can check that out for yourself. You can see that when y is 0, the radius will be 0, but when y is 3, the radius will be 3, and everywhere in between. So the radius is just going to be y. Now, in order to find the height of each cylindrical shell, and maybe height is a misnomer, because the height is actually going to be how long each shell goes. But if you tilt your head sideways or flip your monitor on its side, if you will, then they're heights. And, you know, without loss of generality, it all works the same. So in order to do that, we're going to have to solve this given equation for x. And if we do that, what we'll see is that x is actually equal to, let's see here, what is it? 9 minus y squared. And so that is going to be the height of each cylindrical shell, 9 minus y squared. Check that out for yourself. When y is 0, how tall is that cylinder? Well, it should be 9. And if we plug 0 in here, we do get 9. So that works out quite well. And that would be our first shell. Our last shell is when y is 3. And what should be the height of each shell when y is 3? Hopefully you can see that the height should be 0. And in fact, when we plug 3 in for y in the equation, the height is 0. So this works out rather well. And now that we have this, let's go ahead and set up our volume formula. It's simply going to be 2 pi times the radius times the height. And then, of course, we should include the width of each shell, which is dy. Now, where are the lower and upper bounds for this problem? Well, let's start on the axis of revolution, which is 0. And then we can go out to where y equals 3. And that should do it for us. Now, of course, we can simplify this this integral quite a bit. We could call this 2 pi from 0 to 3 of 9y minus y cubed. And that makes this a very, very easy integral to deal with. And for that reason, I'm not going to do the steps of the integral, but I will tell you that if you do the steps of the integral, you should end up with 81 pi over 2 cubic units as the volume of this paraboloid. So it's really that easy. You just find out, is this an x or a y problem? Once you know, you find the radius and the height in terms of that variable, and then you just set up your equation, 2 pi times the integral of the radius times the height. Work out your integral, you get your volume, and that is a fun and exciting time. So you may now be wondering, why would I ever use this shell method as opposed to the disc or washer method? And if you are asking that question, then example C was written just for you. Example C, we're actually going to take a region and find the volume of that volume of revolution, both using the washer and the shell method. So go ahead, give it a shot before we get there. Pause the video, try it out. To be honest, as long as you can set up your integral, the rest of it should be assumed to be okay. So jump to example C, try working it out, try setting it up rather, using the washer method, try setting it up using the shell method, and you determine which one is easier. When you're ready to see the solutions, go ahead and proceed with the video, and I will meet you on example C. So here's a good time. Example C is actually a two-part example. We're given this region that you see here, composed of the graphs of y equals x squared. That's the lower of the two graphs, and y equals 4x minus x squared. That's the higher of the two graphs, and they make that region that you see there. Now, what we're going to do is take that region and revolve it around the line x equals 2 to come up with the solid that you see here. Now, what we're going to do is find the volume of that solid, which almost looks like the paraboloid once again, but this time there's a hole inside the paraboloid that I can't really show you with this model, but it's a strange shaped hole, kind of, I don't know, it's kind of weird. But either way, we're going to find the volume of that first using the washer method, and then we'll do it again using the shell method, and we'll see which way is easier, and see if I can't convince you that the shell method is sometimes much more effective to use. So anyway, if we are going to begin by using the washer method, then let's go ahead and draw a representative washer, and you see it there. Really all we need to do in order to find the volume of this is simply find the outer radius, which I will call capital R, and find the inner radius, which I will call lowercase r. Now, does this radius need to be in terms of x or in terms of y? We'll simply look at the width of each disk, and hopefully I can convince you that the width of each disk is simply dy, which means that both my outer and inner radii need to be in terms of y. Well, I'm going to start with the inner radius because it's actually going to be a lot easier to find. That's this inner radius right here. And if we're given that this is of the equation y equals x squared, but I need it in terms of y, then hopefully you can see for yourself that this is simply going to be x equals square root of y, and that is going to be my inner radius. That really wasn't that difficult. But as far as the outer radius, this one over here, the way we're going to find that one out is by using the equation y equals 4x minus x squared. And again, we need to solve for x here. Now, this is a little bit more of a challenge. I can't just square root it or, just isolate x or anything like that. I actually need to go ahead and treat this as a quadratic equation of the form x squared minus 4x plus y equals 0. And if I do that, now I can solve for x, and it will be dependent upon y. So let's go ahead and do that real quick. X is going to equal negative b plus or minus the square root of b squared minus 4ac all over 2a. Now, that might be a little bit tricky there that the minus 4ac is actually minus 4y, but recall that c is y in this case. And in fact, if we do work this out, what I'm going to get is 2 plus or minus the square root of, let's see, what is this? This is going to be 4 minus y. So that wasn't exactly easy to do. It was quite a mess, actually. And it actually brings me to a mistake that I made on my inner radius. The inner radius was not quite so easy. The inner radius would be square root of y if I were starting at the y-axis. But because I'm starting at the line x equals 2, my inner radius is actually going to be 2 minus square root of y. My outer radius is going to be 2 minus this garbage that I got down here. So 2 minus 2 plus or minus the square root of 4 minus y. All right, that is quite ugly. Fortunately, it can be simplified just a little bit. Let me go ahead and call that the square root of 4 minus y. I'll ignore the plus or minus in front of the radical. And if you play a few games with it, you'll see that it's always going to be positive up here if I make it negative to begin with. So distribute that. I get the square root of 4 minus y. My inner radius is 2 minus square root of y. And now I think I'm ready to go. If I want to set up my volume formula, my volume is simply going to be pi. I'm going to start at 0 and proceed up to 4 with my disks. So I'll go pi from 0 to 4. My outer radius squared, which will be the square root of 4 minus y squared, subtracted by my inner radius squared. So that's 2 minus square root of y squared. And then, of course, dy. Now that is quite hideous. Actually, it's not as bad as you might think. It's pretty bad. But if we simplify this just a little bit, This is pi from 0 to 4. I actually did work this problem out earlier here. And if we simplify this out, what we're actually going to get, if I did this correctly, which I hope I did, is 4 square roots of y minus 2y dy. That we can work out, that you can do on your own. And if you do it correctly, what you should obtain for your result is 16 pi over 3 cubic units. So it wasn't that bad once we got the integral set up. However, setting up the integral was hideous. We had to use quadratic formula. We didn't even have a c. We had to stick y in there for c, solve for that, square a bunch of things. We had to deal with the fact that the axis of rotation was x equals 2 rather than the standard x equals 0. You can see that reflected in my 2 radii right there and right there. That's why I have 2 minus in each case. Worked it out, and pi times outer radius squared minus inner radius squared. Now, once I got it set up, it wasn't so bad, but setting it up, that was a bear. So, regardless of that, we did get the correct answer, 16 pi over 3. But let's go ahead and try this problem one more time using the shell method and see if it isn't any easier. So let's go ahead and wipe all this problem out and start over again here. So in order to find the volume of the solid using the shells method, I've gone ahead and skipped all the steps of drawing it. You've already seen what the solid looks like. And I've already drawn a representative cylinder for you here. So we can go ahead and begin by deciding, is this a dx or a dy problem? So if we look at the width of the shell is the width of this black segment here, or this black segment here, if you will. Either way, that is going to be dx as the width of our cylinder. And so everything has to be in terms of x. Now, we don't need to worry about an inner radius or outer radius here. None of that is applicable. All we really need to find is the radius of each shell, and that will be in terms of x. And we also need to find the height of each shell in terms of x once again. So what is the radius of each shell? In most cases, well, in our last 2 examples anyway, we just said x or y, whatever the case may be. But notice that our axis of revolution this time is the vertical line x equals 2. And so what that means is that our radius is actually going to be 2 minus x. To see why that's the case, when x is 0, notice that the shell will have a radius of 2. That would be this shell right here on the bottom. That's kind of outlined by the three-dimensional nature of the solid itself. So that has a radius of 2. When x equals 2, our shell will have a radius of 0, which will be that shell right there that you can barely see because it has a radius of 0. Plug both of those x values into the radius, and you'll see that they do both hold, so that's good news. Now, what is the height of each one of these cylindrical shells? That's actually very easy to do. It's just going to be the top function subtracted by the bottom function for each value of x along this interval. That's actually going to be quite easy here. The top function in each case is just 4x minus x squared. And the bottom function in each case is just x squared. So what that tells us is that the height of each of these cylinders is just going to be 4x minus 2x squared. And we now have all the information we need in order to set up the volume formula for the shell method. It'll look like this. The volume will be 2 pi times the integral of the radius, which again is 2 minus x, multiplied by the height, which in this case we just determined is 4x minus 2x squared. Of course, don't forget your dx, that's the width of each cylinder. Now, where will be our lower and upper bounds? Well, let's start at 0 and go to the axis of revolution, which is 2. And so I'm going to put 0 to 2. You might ask yourself, what if I went from 2 to 4? Would that work out? And for that, of course, I'll say go ahead and give it a shot and see what happens. It's really best just to stay with the region that we were originally given. And that's why I'm going to go from 0 to 2. Now, of course, we can simplify this integral just a little bit. 2 pi times the integral from 0 to 2. If I multiply out these two binomials, if I did this correctly, what I should get is 8x minus 8x squared, and then plus 2x cubed. And I've gone ahead and just multiplied those out beforehand, but that's what I got. And that is a very, very simple integral to evaluate. In fact, if we integrate that and work it all out, what we should get, and what I got when I did this earlier, was 16 pi over 3 units cubed. Does that volume sound familiar? Well, of course, it was the same volume that we got when we did this exact problem using the washer method. But my question to you, which method seemed easier? And that should be fairly obvious. Of course, both ways work, so I'm not telling you that you have to do one way over the other, although sometimes that is the case. But even when you can apply both methods, one method is usually much easier than the other. And there you go. So here in lesson 6.3, again, we didn't cover a whole lot, but what we did cover was extremely important. Simply another method to finding volume of solids of revolution, this time using the cylindrical shell method. Now, one thing you might notice is that when we're using the washer method, the variable that we use is always going to be perpendicular to the axis of revolution, although when using the shell method, the variable that we use is always the same variable as the axis of revolution. Or rather, if you want to put it this way, it'll be whatever is parallel to the axis of revolution. And that makes sense because essentially we're going like this with the shells. All right, so of course, you don't need to remember that if you're good at drawing pictures, and that really is my first piece of advice. When you're doing any volume of revolution, whether it's washer or shell method, you should always draw your region first, draw the solid of revolution, and then draw a representative figure. If we're doing the washer method, draw a representative washer. If we're doing the shell method, draw a representative cylindrical shell. Once you've done that, you can determine is the width of that shell a dx or is it a dy, and that will guide the rest of your work. Once you've determined whether it's dx or dy, all you need to do is find the radius and the height of your representative shell in terms of the correct variable, and then you can just set up your volume formula, which is just the integral of 2 pi rh. 2 pi rh, remember, is just the surface area of each cylinder. So really all we're doing is just adding the surface area of every cylinder together, and that will give us the solid that we're looking for. So remember all this as you are working on this assignment, and as always, good luck.